So we have this square lamina of mass m, which is hinged at A and is supported by a string at B to the ceiling. Now, this string is snapped, and we want to be able to compute just after snapping this string. We want to be able to compute the angular acceleration of the plate, we want to compute the acceleration of the corner C, and we want to compute the reaction at A. Right? This is what we want to be able to do. Now, first of all, if I snap this string at B, it's pivoted at A. So then this whole thing will be in a state of pure rotation about A. This whole thing, the lamina would be in a state of pure rotation about A. Right? This is the center of mass. There is a torque about A. Now forces acting on the lamina, by the way. If you look at the free body diagram of the lamina, there is mg acting like this. And at A, you would expect a vertical reaction and a horizontal reaction. You would expect, let's say, a vertical reaction Ry and a horizontal reaction Rx. And it's going to get into a state of pure rotation about A. Now, there is a non-zero torque about A, which is produced by mg. Rx and Ry will produce no torque about A, but mg produces a torque which is mg into this length, this is L by root 2. So if I take torque about A, I'm ready to compute alpha. If I take torque about A, I'm ready to compute alpha, the angular acceleration alpha. So torque about A is mg into L by root 2 is I about A. Now, what's I about A? For a square lamina, what's I about A? Okay, answer this. What's I about the center of mass? 1/6 ma squared. So 1/6 ma squared plus m into L by root 2 whole square. Parallel axis theorem, yes or no? So I about A is 1/6 ml squared plus m into L by root 2 whole square. That's parallel axis theorem. I about A into angular acceleration. Clear? So this gives me like a g by root 2 equals L into 1 by 6 plus 1 by 2 L by 3 into alpha. Right? So I get alpha equal to 3g by 2 root 2 L. These many radians per second squared is the angular acceleration, right? That's 1. Now, come to the point C. What's the acceleration of the point C? Very simple. This is A. All points on the body, since it's in a state of pure rotation, all points will have the same angular acceleration. All points will move in a circle centered at A. So C moves in a circle centered at A. That means radius CA. right? And this length is L root 2. So the acceleration of C will be perpendicular to the radius, will be L root 2 alpha, right? That's going to be L root 2 alpha, so which is like 3g by 2. 3g by 2 meters per second square, right? Now come to the reaction at A. Realize that it's easy to figure out Ry. Ry is because the center of mass has an acceleration ACM, which would be L by root 2 into alpha, right? That's going to be the acceleration of the center of mass. Now, what causes the acceleration of the center of mass? Net of all forces in the vertical direction acting on the lamina. That means mg minus Ry is responsible for ACM. ACM is the baby of mg minus Ry, right? So mg minus Ry is instrumental in producing ACM. ACM we have already known. ACM is L alpha by root 2. 3g by 4, I guess, right? So Ry is ready for computation straight from this equation because ACM is known, right? But why should there be an Rx? Why should there be an Rx? Can anyone explain to me why should there be an Rx? Ry is because there is an ACM downwards. What about Rx? Now that's exactly what I realize, that it starts from rest. So velocity of the center of mass is 0, right? And the center of mass, it has a centripetal force requirement which is 0. And if it was non-zero, it would have been met by Rx. But since VCM is 0, Rx, which is m VCM squared divided by this radius r, will be 0. So Rx in this case is 0. Right? So we have this slender rod of mass m and length L, supported symmetrically by 2 springs as shown, and we eventually snap spring 2, and at the instant when we snap, we want to be able to compute the angular acceleration of the bar, we want to be able to compute the acceleration of the point A, and we want to be able to compute the acceleration of the point B, right? This is what we want to be able to do. First of all, let's look at the state of the 2 springs just before the spring 2 is snapped. Both the springs would have undergone the same amount of elongation, right? So let's say this spring elongated by an amount x to get into this position, same with the spring. So then there would have been a spring force kx like this, and there would have been a spring force kx like this acting on the rod, and the vertical components of kx supported the weight. The horizontal components cancelled off in pairs, right? So then we have 2kx sine 30 degrees supporting the weight, and therefore kx being equal to mg. So the force in each spring was kx equal to mg before spring 2 was snapped. This is easy, right? Now we snap this spring. And let's say this is the point where this spring 1 is connected to the rod. Very clearly, the spring is a non-impulsive element. It's a non-impulsive element. So the force in the spring Kx, right after you snap, spring 2 is not going to change instantly. The spring will maintain status, and as far as x is concerned, just before and just after, it's going to maintain the same status, right? So this spring will be Kx. Will still be a Kx. Now, what are the forces acting? What are the forces acting? The forces are, there is like a Kx sine 30 degrees, a Kx cos 30 degrees, and there is an mg. This is the summary of all forces acting. So the forces acting on the rod right after spring 2 is snapped, T sine 30 degrees upwards, that means T by 2, Kx is T, so T by 2 upwards, and T cos 30 degrees parallel to the rod, that means T root 3 by 2. This is the point P. The center of mass C is like L by 6 away from P, is L by 6 away from P. And there is mg acting to the center of mass, right? This is the summary of all forces acting on the rod AB. Now, I want to be able to compute the angular acceleration. Obviously, I'm looking then at the prospect of applying tau equal to I alpha. I'm looking at the prospect of applying tau equal to I alpha. One thing that I mentioned in the past and I repeat, the points about which you can apply tau equal to I alpha. 1, the center of mass always indiscriminately. 2, the instantaneous center. Now in this case, when a body starts at rest, you don't talk of an instantaneous center at that instant, essentially, right? I can't apply about the point P. The point P, realize that even though it's at zero velocity, it has a non-zero acceleration. It has a non-zero acceleration, the point P. Because it's a spring, it's ready to succumb to the forces. It's ready to wax and wane, right? So there is a non-zero acceleration associated with the point P. Do you have a clear-cut instantaneous center associated with it at this instant of time? I mean, it's starting from rest, then what's the instantaneous center? Nothing like an instantaneous center. Which means now you want to be able to apply, tau equal to I alpha about the center of mass, right? So in order to be able to compute alpha, realize that T root 3 by 2 passes through C and produces no torque about. Whereas T by 2 produces a clockwise torque, T by 2 into L by 6. T by 2 into L by 6 in the clockwise sense, producing an alpha, right? So then, in order to compute alpha, you take torque about the center of mass, which is T by 2 into L by 6, so TL by 12, that's torque about the center of mass divided by I about the center of mass, which is 1/12 ml squared, which is 1/12 ml squared. But T we have computed as mg already. So then this becomes like a g by L radians per second square, the angular acceleration, right? G by L is the angular acceleration. So we have this ready with us. Now, once we have set up the angular acceleration, See, now it's no longer in pure rotation, by the way. After you snap spring 2, unlike the earlier situation, this will not be in a state of pure rotation because this will not be a fixed point. It's a spring. It's not going to be a fixed point, right? It's going to nudge. It's not a hinge either. So it would get into a general rigid body motion. This rod would get into a general rigid body motion characterized by two things. One, an alpha, which we've already computed. Two, an ACM. These two things put together would characterize the complete acceleration field of the rod AB at this instant of time, right? So the task in hand is to compute the ACM at this instant. To compute the ACM at this instant, you would have to look at all the vertical forces acting on the rod and all the horizontal forces. Now, it's not like ACM will be just vertical in this case. It's going to be mg minus t by 2, which will cause the vertical acceleration of the center of mass, and then t root 3 by 2 would cause a horizontal acceleration of the center of mass. Yes or no? In this case, the center of mass is not going to fall vertically downwards. It's going to have a vertical acceleration because of the difference of these two, and it's going to have a horizontal acceleration because of t root 3 by 2, right? So then, let me call this the x direction and this the y direction. So the acceleration of the center of mass, in the y direction is going to be mg minus t by 2. T we have computed as mg, right? T we have computed as mg. So mg minus t by 2 divided by m. So it turns out to be g by 2 meters per second squared in the vertical direction, right? Ax is caused by t root 3 by 2 acting horizontally. That's the net horizontal force acting on the system. So t root 3 by 2 divided by m. So that makes it like g root 3 by 2 meters per second squared in the horizontal direction. And alpha we've already computed as g by l, right? So we are all set to compute the acceleration of various points on the rod with this data available, right? For the center of mass, there is horizontal acceleration g root 3 by 2, and there is a vertical acceleration g by 2, and there is an angular acceleration alpha, which is g by l. So if I have to now compute the acceleration of the point A, this length is L by 2. So because of pure translation, it will have like a g by 2 like this and a g root 3 by 2 like this. It will share with the center of mass because of pure translation. Both in the horizontal and vertical direction, it will share a common acceleration with the center of mass. Now, imagine it to be in a state of pure rotation with angular acceleration alpha about the center of mass. Then it's going to have an acceleration because of tangential acceleration, which would be L by 2 into alpha upwards. So L by 2 into alpha upwards, which again is g by 2. So these are the various acceleration states of the point A in suggested directions. So in the vertical direction, A has 0 acceleration. In the horizontal direction, A has g root 3 by 2. So as far as A is concerned, acceleration of A in the x direction is g root 3 by 2. Acceleration of A in the y direction is 0. That's for the point A. Right? For the point B now. Same thing. This point B has a common acceleration with the center of mass g root 3 by 2 in the x direction, g by 2 in the y direction. Now it's in a state of, imagine it to be in a state of pure rotation about the center of mass. So it will have a tangential acceleration L by 2 alpha, which would be G by 2, which would be G by 2. So the net acceleration in the y direction, this becomes G by 2 plus G by 2, which is G. So for B, the net acceleration in the x direction is G root 3 by 2, and the net acceleration in the y direction is G. And likewise, we could compute the acceleration of any other point which included that point P where the spring 1 was connected to the rod. Exactly the same manner by superimposing pure translation with pure rotation. Good. Fairly simple. There is this rod of length L, and it's struck at the lowermost point by a sphere of mass m with a velocity v0. And the rod is hinged at A. The impact is characterized by coefficient of restitution being 0.8. Right? That's the impact. Means the sphere, let's say, the sphere after the impact has a velocity v. It does not stick to the rod because E is not 0, right? And this gets into a state of pure rotation about. So then the rod is completely characterized by omega. The rod is completely characterized by omega. Now realize that the force that the sphere exerts on the rod is equal and opposite to the force that the rod exerts on the sphere, and they exert the torque of these two forces about A add up to 0. One produces a clockwise torque about A, the other one produces an anti-clockwise torque about A, the forces that they exert on each other. Therefore, the net torque about A is 0. There is a reaction at A, but then that reaction at A will produce no torque about A. So, the torque because of the impulsive forces that they exert on each other is 0. So, which means this would make us eligible to apply conservation of angular momentum about A. So, just to begin with, the sphere brings to the system an angular momentum mv0 into L. That's the total angular momentum of the system before and after. And this does not depend on the nature of collision, right? What remains in the sphere after collision is mv into L, and the remainder is available to the rod, which is I about A into omega. I about A is what? 1/3 capital M into L squared into omega. There are two unknowns, V and omega. And obviously, I have one condition pending. The nature of collision, E is 0.8, has still not been deployed. So what I do is realize that just before collision, the sphere has a velocity v0, and the point of impact P, has a velocity 0 just before collision, right? Just after collision, the point P would have a velocity L omega, whereas the sphere would have a velocity v. So then, to apply E equal to 0.8, relative velocity of separation divided by relative velocity of approach. So I take sphere minus this in the numerator, so V minus L omega in the numerator, and then in the denominator, I'll take P minus V0. That means 0 minus V0. It gets swapped. So with these two equations put together, you can solve for V and omega. See, there is this disk. It starts from this state, moving to the right with a constant velocity v, and having a constant angular acceleration beta with initial angular velocity 0. After a while, let's say this is at time t equal to 0. Now t seconds later, the center of mass would be at x0, it would have x, where x would be v into t. X would be v into t because it's moving with a constant velocity. And at this instant of time, its angular velocity omega would be omega naught plus beta t, omega naught plus beta t. So it's going to be beta t would be its angular velocity, right? I want to be able to locate the, I want to be able to assess the path traced by the instantaneous center with these kinds of velocities and angular velocities. Realize that if I took a point P, what I do is, look, I told you in the past that the instantaneous center does not necessarily lie on the body. It could lie outside the body. Now, what that really means is that if a body is in general rigid body motion, characterized by what? Characterized by two things, the VCM and omega. From instant to instant, the velocity field within the body is characterized by VCM and omega. Now, what I do is, if this is a lamina, then I include the entire plane to be part of this lamina. The entire plane would have a velocity field governed by the VCM and omega that this produces. Imagine that the entire plane is moving. You know, there is a layer of plane which is moving inside a fixed plane. So every point on the moving plane would be guided by the motion of the lamina. The VCM and omega that the lamina imparts would produce velocities of different points on that extended plane. I just imagine that. And in the process, be it on the extended plane or be it on the body, I can suitably identify a point P from instant to instant that has zero velocity, and that point P is referred to as the instantaneous center, right? Now, so this is one point on the extended lamina which is moving under the dictation of the disk, right? The VCM and the omega of the disk will dictate the velocities of various other points in the surrounding region. I'm imagining that the plane itself is moving along with the disk governed by the VCM and omega. So I can associate velocities with different points outside the disk also. So now, at this juncture, let's say there is a point P, x comma y. This would have a velocity v to the right. If I want to compute the velocity of this point, I would superimpose pure translation with pure rotation. Because of pure translation, it's going to be v to the right. Next, imagine it to be in a state of pure rotation about the center of mass, like this. So it will have a tangential velocity which would be omega times y, because this length is y, this length is y. So omega times y leftward. You can identify a y such that v would be equal to omega y, and then this point would be the instantaneous center. If v becomes equal to omega y, then the point P is the instantaneous center. So for P to be the instantaneous center, v must be equal to omega times y. Yes or no? Where omega is bt, and in t seconds, the horizontal displacement is x, carried out with a constant velocity v. So t must be x by v, So which gives me xy equal to v squared by beta. V is a constant, beta is a constant, so right hand side is a constant. So the x and y coordinates of the instantaneous center would always be connected by this relationship xy equal to constant, and therefore the path traced by the point P is a hyperbola, rectangular hyperbola. Hyperbola is the path traced by the instantaneous center. The locus of the instantaneous center is a hyperbola then. Clear? The next part of the problem, similar stuff, part B. The disk moves with a constant acceleration a, with initial velocity u being 0, while the disk rotates counterclockwise with constant omega. Counterclockwise with constant omega. So it maintains omega now. So after a while, t seconds later, the angular velocity of the disk will still be omega, whereas its linear velocity v would be a into t. Linear velocity would be v equal to a into t. Under these revised conditions, I want to now find the locus of the instantaneous center. Again, if this is the instantaneous center, v must be equal to v omega at that instant into y, so that the net velocity of the point P is 0. Right? Now, very clearly, if I square, v squared is omega squared times y squared, omega squared times y squared. Since it's in a state of constant acceleration, v squared must be 2ax. V squared must be 2ax. V squared is u squared plus 2a into the displacement in the direction of v, which is x. So v squared is 2ax. That's omega squared y squared. So we very clearly have y squared equal to 2a by omega squared into x. 2a by omega squared is a constant, and therefore, what locus does this represent? A parabola. So the path traced by the point P is a parabola. The locus of the instantaneous center is a parabola. I mean, no, you don't have to say that. I mean, it's in the first quadrant, in the sense that yes, it's part of that curve only. This is all right. I mean, what he's saying is, I can be technically correct by saying this is y equal to root 2a by omega squared into root x, so that the locus is confined to the first quadrant. But that's all right. That's not a necessity. You can still say that this is the locus. It's not essential that all points on the locus be covered. Right. I mean, for example, in projectile motion, do you cover all points? But you still say y is x tan theta minus gx squared by 2u squared cos squared theta. Isn't it? Not all points are covered. It doesn't go below the plane. But the locus is still that parabola, right? So then, the disk or a sphere? Sphere. Okay. So now the sphere is set into general rigid body motion characterized by v naught and omega naught. Naturally, it's not rolling right now because the velocity of the lowermost point is to the right, v naught plus r omega naught. Right? So frictional force would duly act to the left, mu k times mg. It will have a leftward acceleration, which would be mu k times g would be the leftward acceleration of the center of mass. Now, what is this Fk doing? It's killing VCM, and it produces an anti-clockwise torque about the center of mass. Sorry, a clockwise torque about the center of mass, which opposes this anti-clockwise omega naught. So it's killing omega naught as well. So both VCM and omega naught are getting killed. There are three possibilities. Possibility 1. Omega gets killed prior to VCM. It gets into a state of pure translation, and eventually a pure translation would culminate into pure rolling down the line. That's one possibility. Possibility 2. It kills VCM first, leaving a residue of omega, and then it gets into a pure rotation, and pure rotation eventually would also culminate into pure rolling down the line, and it will never come to rest. So the first two states will never bring the sphere to rest permanently. Is 3. When both VCM and omega simultaneously become 0, then there is no pending motion beyond that point. It will come to rest permanently. So for the body to come to rest permanently, VCM and omega have to simultaneously become that's the only possibility, right? Now, irrespective of whatever is happening, realize that Between this state and this state, obviously, it's never rolled. It's always flipped. Because if it had rolled, it would have continued to roll forever. So it never rolled. Frictional force acted leftwards, mg acting downwards. Both the frictional force and mg have their lines of action passing through the point of contact. So they end up producing no torque about the point of contact. And therefore, between these two states, the angular momentum about the point of contact must be the same. Yes or no? Right? So between these two states, anywhere between these two states, the L about the point of contact must remain constant. Why? Because torque about the point of contact is now the rightmost state, the final state, gives us a very clear-cut insight into what the angular momentum about the point of contact must have been all along. Realize that it's at rest. Both VCM and omega are 0, so the angular momentum about the point of contact must have been 0. Yes. So the angular momentum must have been 0 all the way. And it must have been 0 here also to begin with. It must have been 0 here as well, right? And what's the angular momentum here? Well, let me take clockwise positive, anti-clockwise negative. So mv naught into r clockwise minus ICM omega naught anti-clockwise. Right? Where ICM is 2/5 mr square, and this then would be the defining relationship between V naught and omega naught for the rest, permanent, for the sphere to come to rest permanently, right? And obviously then the time taken for the center of mass of the sphere to go from V naught to 0 under the influence of a retarding acceleration mu kg is going to be what? V naught divided by mu kg. That's going to be the time taken. Yes or no? Applying V equal to U plus AT. V is 0, U is V naught, and A is minus mu kg. So T becomes V naught by mu kg. That's the time taken for the velocity of the center of mass to become 0. And at the same instant, the omega also becomes 0. Simple. There is this uniform disk in general rigid body motion characterized by V naught and omega naught, and suddenly the topmost point is fixed. When the topmost point is fixed, one has to apply a force at the topmost point. But when you apply a force at the topmost point, then that force produces no torque about the topmost point. So the torque about the topmost point is 0. It's 0, right? And therefore the angular momentum about the topmost point must be. Now, once you fix it at A, what's the nature of motion exhibited after that? Pure rotation about A. So it means angular momentum about A in this state must be equal to angular momentum about A in this state. Angular momentum about A in this state. Let me take anti-clockwise positive and clockwise negative. So anti-clockwise momentum, this mv naught, V naught will produce mv naught r anti-clockwise minus ICM omega naught clockwise. That's the net anti-clockwise moment about A. Prior to fixing it at A, and after you fix it at A, well, it's in a state of pure rotation about A, and then the angular momentum about A is simply going to be I about A into omega. And what's ICM? ICM for a disk is half mr squared, and therefore what's I about A? Half mr squared plus mr squared. Parallel axis theorem, half mr squared plus mr squared, 3/2 mr squared. So that will give you the omega of the disk after you fix it at. Clear? No, rotation is not stopped. Now rotates about it. No, the velocity field will change such that now every point will move with A as the center. So it will develop a new omega. See, what really happens is now, so what if I'm fixing it at A? I mean, you are getting confused because every point will have a velocity which would be the superimposition of pure translation and pure rotation. So what if I fix it at A? I mean, the sense of omega changes. Huh? If it was a thread, what was the minimum velocity required? Root 5 g. That's not a thread, it's a rod. It's not going to be root 5 gs anymore. Let's understand why. But again, basic physics with it is what? If you impart it a small velocity, right, then it will only oscillate about the hinge. But if you can impart it a good enough velocity so that it becomes vertical, it just about becomes vertical, B goes to B prime. And if it just about becomes vertical, then it's capable of completing the full circle, right? The velocity should be just enough so that the rod becomes vertical eventually, right? Now, the rod could be replaced by a point mass m at its center. So the center of mass of the rod plus the particle, both are of the same mass, would lie at O, which is halfway between C and B, but C and B is L by 2. So halfway between C and B is like L by 4. That's the center of mass of the rod particle system. Right? L by 4 from the bottom, or 3L by 4 from the top, So which means now you expect O, which was 3L by 4 below A, to be 3L by 4 above A. So now point O would be expected to be 3L by 4 above A. Right? So then, energy principles, right? Energy principles. What's the loss of potential energy when O goes from O to O prime? You can imagine a total mass 2m. To have got elevated by an amount 3L by 2. 3L by 4 plus 3L by 4, 3L by 2. So what's the total gain? In potential energy if it has to just go about in the vertical? So it's going to be 2 mg into 3L by 2. Right? Now, gain in potential energy must come at the expense of loss of kinetic energy. What's the kinetic energy that you're imparting here? The particle at this point has half mv squared, The rod has half of I about A into omega squared, because the rod develops an omega. So for the rod, half of I about A into omega squared. I about A is 1/3 ml squared for the rod. For the rod alone, this was particle alone, this was rod alone. And what's the omega? Look, the lowermost point of the rod has the same velocity as that of the particle, and the rod about A has an angular velocity omega. So do you realize that omega must be V by L? Yes or no? Because this point is in a state of pure rotation about A, so V must be L omega. So this omega can be written as V by L. IA could be written as 1/3 ml squared, and then you are ready to calculate V, the minimum velocity required. Got me? Hey, this equilateral triangle, side A, and at the topmost point a force F is applied, and it's given that mu is very high. Mu very high actually implies that it cannot slide. The value of F that you apply here would be countered by the frictional force, so it's not going to slide. The triangular prism will not slide, but it will have a tendency to topple about C. It's going to have a tendency to topple about C. Realize that this length is a root 3 by 2, this is a by 2. This F about C will produce a clockwise torque, whereas mg about C will produce a restoring anti-clockwise torque. So if the torque of F just about exceeds the torque of mg about C, then it's going to topple about C. So for it to topple about C, the torque of F about C is F into the moment arm, which is a root 3 by 2. F into a root 3 by 2 is the torque about C that F produces. And if it just about exceeds the torque because of mg about C, that means mg into a by 2. So F greater than or equal to something, this will be the F minimum. The right hand side would be the F minimum required to topple it about. When they say rough and they don't exactly quantify, they actually mean rough enough to promote rolling. That's what it means, right? So there is a perfectly inelastic collision occurring with the disk at rest, same mass, radius r. We want to be able to find the angular velocity of the disk subsequent to the impact. Right? Now, realize that just after the impact, for the disk alone, there is a VCM and there is a omega. For the disk alone, where VCM is the velocity of the center of mass of the disk, not the disk plus the particle, just the disk alone. And this point P where the mass gets embedded, would have a velocity commensurate with the combination superimposition of VCM and where because of rolling without slipping we have VCM equal to R omega, right? So this point P on the disk as well as the mass which gets embedded, it has a velocity VCM because of pure translation and because of pure rotation about the center of mass O of the disk. This has an R omega like this. It has an R omega which is the same as VCM, which is the same as VCM. How about it? Now, realize when this impact occurs, there is a frictional force that acts here. But it produces no torque about this point. Mg also passes through this point, which means before and after the impact, the angular momentum about the point of contact must be. Now, what does this mass bring in terms of the angular momentum about the point of contact? Mu into R clockwise. It brings mu into R clockwise about the point of contact, right? Angular momentum about the point of contact brought by this mass to the system is mu into R clockwise. Right? The mass m subsequent to the impact has a VCM like this and has a VCM like this. Just the mass alone, mass small m, has a, because it gets embedded, so it shares the same velocity as the corresponding point on the disk, corresponding point P on the disk, right? Which has a VCM like this and a VCM this way. So the mass m has angular momentum m VCM into R clockwise. Because of this, it's m VCM into R clockwise. plus this VCM is also like MVCM into R clockwise. Yes or no? This VCM also produces MVCM into R clockwise about the point of contact. This length is R, right? So that makes it 2 MVCM into R for the mass alone about the point of contact. And now for the disk about the point of contact is going to be MVCM into R plus ICM omega plus ICM omega. ICM is MR squared and omega is VCM by R, or you can write we want to be able to compute omega, right? So you can write this VCM as R omega. So this is like 3 MVCM R plus ICM omega. VCM you can write as R omega and solve for omega. Is it A? Is it A? It's not A? Huh? Right. 2 by 7. Is there anything else that you did in this problem? Similar? Can I wipe this off? So we have this sphere, solid sphere of radius r, and initially it's given pure translation. VCM. The VCM here is related to the omega there. This is a state of pure rolling that it acquires after a while, right? In which it has a VCM and an omega. But the initial VCM that it is given is like 2 times r omega, where omega is the angular velocity at the instant of pure rolling, right? We want to be able to find out the time it takes for the body to start rolling. Now, very simple, because it has an acceleration which is like mu g to the left, right? Because of frictional force, it has an acceleration mu g to the left, and the VCM at any given instant of time t is going to be given by initial velocity 2r omega minus mu gt, right? The alpha that is produced at any given instant of time, the alpha that is generated because of the frictional force is mu mg into r is the torque, mu mg into r is the clockwise torque, divided by I about the center of mass, which is 2/5 mr squared. That's going to give me the angular acceleration clockwise, which is 5 mu g by 2r is the clockwise angular acceleration, right? Yeah, bolo. 5 mu g by 2r, right? So the omega obtained t seconds later would be alpha t. Alpha t would be the omega t seconds later. Omega would be omega naught plus alpha t. Omega would be omega naught plus alpha t. And then in the even, this is a state of pure rolling. VCM would be equal to r omega. VCM is like 2r minus mu gt. VCM equal to r omega. And r omega is 5 mu gt by 2. So you will get the time when pure rolling starts. Simple. I expected you to have got it right independently. All right. Again, have you got this right? What's your answer? Let's. So from this state to that state, the angular momentum about the point of contact is conserved, right? So angular momentum in this state is mv naught r plus the sphere, solid sphere. So 2/5 mr squared into omega naught 2v naught by 3r ICM omega, that's the angular momentum about the point of contact here, must be equal to angular momentum about the point of contact. It would be, which essentially would be the same as the angular momentum. You can imagine this, since it's gotten into a state of pure rolling, you can imagine this whole thing to be in a state of pure rotation about the point of contact. This becomes the instantaneous center, right? So I becomes 7 by 5 mr squared, right? So I times omega, the angular momentum about this is going to be I about this point into omega, or you could have said mv into r plus ICM omega, where v is r omega. You could have done that, right? But then in one shot, it's going to be 7 by 5 mr squared into omega. You can imagine it to be in a state of pure rotation about the instantaneous center with angular velocity omega. Then the angular momentum about this point is going to be I about this point into omega, or mv into r plus ICM omega, where omega is BCM by r. Either way you want, right? So, so this will give you omega is v by r. Omega is v by r. So this will give you v in terms of v naught. This will give you v in terms of v naught, right? And then the omega goes as omega equal to initial omega naught plus alpha t, right? But the omega there is like a v by r. The omega here is like a v naught by omega naught here is 2 v naught by 3r, right? And the angular acceleration, realize that frictional force, as we've all computed, is mu mg into r, that's the torque, divided by 2/5 mr squared. Or what you can just do is, you can compute alpha in terms of t. You can compute alpha in terms of t. V we know in terms of v naught. So I can write v naught in terms of v. So I would know alpha in terms of t from this equation. I would simply know alpha in terms of t from this equation. And once I know alpha in terms of t, and therefore, you know, also in terms of v, because I know v naught in terms of v from this equation. So I would know alpha in terms of v and t completely from this equation. Yes or no? Right? And then what's the angle rotated? Theta would be omega naught t plus half alpha t squared. That would be the angle rotated in t seconds. That would be the angle rotated in t seconds, where alpha is known in terms of t and v from this equation. Omega naught is known, and you will get the angle rotated in. And realize that alpha would have 1 by t here, so that will make it into t. So you can take t common, and there would be a v and t combination appearing, right? And he's done the calculation. He says A is the right answer. A is the right answer. You still maintain that A is the right answer? So you might want to check these calculations. Very simple, right? You know v naught in terms of v from this equation. So this v naught you can plug in terms of v. So alpha known in terms of t and v from this equation, and you can plug into this, get the angle rotated. So about the ridge, all that you do is you preserve angular momentum. So initial angular momentum about the ridge is mv into a by 2. mv into a by 2 is the initial angular momentum about the ridge. And then once it starts to topple about the ridge, that means it gets into an angular velocity omega about the ridge. Then this is the center of mass. So then the angular momentum about A is simply going to be I about A into omega, I about A into omega. Right? Topple means it gets into a state of pure rotation about A with an angular velocity omega. So you preserve angular momentum about A, and this is what happens. And I about A is what? ma squared by 6 plus m, this is A by root 2, A by root 2 squared, mr squared. That's parallel axis theorem. Parallel axis theorem. Simple. What's the answer? Agra. An impulse is applied to the NP, a force for a short time, which results in a VCM, and this impulse produces an anticlockwise angular impulse about the center of mass. So that results in an anticlockwise omega. Angular impulse produces omega, and linear impulse will produce VCM. Right? So, what's the angular impulse about the center of mass? P into L by 2 is the angular impulse, right? P into L by 2, the angular impulse, must be change in angular momentum about the center of mass. Final angular momentum about the center of mass is ICM omega. Initial angular momentum was. So, ICM is 1/12 ml squared. So, omega is the omega just after the impulse. Just after the impulse, this is the angular velocity omega. And so the orientation of the rod takes place commensurate with omega. The time taken to rotate by 90 degrees would be 90 degrees divided by the rate at which the rotation occurs. Total rotation divided by the rate at which the rotation occurs, that will give you the time it takes to rotate by 90 degrees. Again, I expected you to get this right. So we have this light rod and connected to two identical spheres, A and B. Mass m, radius r. This wall is smooth and this is pretty rough, so that rolling could occur for the sphere, right? The system starts from this vertical position. After a while, this one descends and this one moves to the right. Find the velocity of the midpoint of the rod when theta is 60 degrees. For a certain theta, you want to be able to find the midpoint of the velocity of the rod. Now, few things. When this descends down, there is no torque acting on it. Why? Because there is no friction. And the rod at this point will not produce any torque because it's attached at the midpoint. So it's not going to produce any torque, right? So there is no torque acting on this. So there is no omega that develops on it. It simply translates down. While this moves into that position, this only translates down with varying velocity, right? But it does not develop any omega. So by the time this A reaches this position, let's say it has a velocity VA downwards, right? This translates as well as rotates. This gets into general rigid body motion, and because the floor is rough, it has a motion completely characterized by VCM and omega. Such that from instant to instant, VCM is R omega. Let me call this VB. Now, from this state to this state, the entity A has lost elevation. It was at a height L. Now it's at a height L cos theta. So the elevation that it has lost is L minus L cos theta, resulting in loss of potential energy for the upper sphere, right? Now the lower one rolls, there is friction, but this frictional force does no work. Because it does no work, it does not participate in the energy equation, right? So that means there is energy conservation. All the potential energy that is lost goes towards gain of kinetic energies of these two. Friction is not doing any work here because it's rolling. So this must have gone towards half m VA squared plus half m VB squared, kinetic energy of rotation also, half ICM omega squared. Where Omega is VB by R. Omega is VB by R. Right? The second thing is, realize that if this was the rod, two ends of the rod, A has a velocity VA like this, and B has a horizontal velocity which is VB like this, right? And this is part of, these are 2 points on a rigid rod. Theta, very clearly, the relative velocity of A and B along the rod must be 0. That means velocity of A along AB must be equal to velocity of B along AB, right? Velocity of A along AB is VA cos theta, must be equal to velocity of B along AB, which is VB cos 90 minus theta, that is VB sin theta. So VA is VB tan theta. So then you know VA and VB from these two equations. You know VA and VB from these two equations that theta equal to 60 degrees, right? And now if you want to compute the velocity of the midpoint of the rod at this juncture, what would you do? You know the velocities of these 2 points, what would you do? One is the instantaneous center. Yes. The other thing that you could do is, at any given instant of time, if this had coordinates x comma 0 and this had coordinates 0 comma y, then the coordinates of the midpoint xm ym would be xm would be x by 2 and ym would be y by 2, right? If I differentiate this, I get the x component of the velocity of the midpoint. If I differentiate this, I get the y component of the velocity of the midpoint. So when I differentiate this, x dot m, that's going to give me x dot by 2. X dot is VB. X dot is VB. Yes or no? So this is VB by 2. X component of the velocity. Whereas when I differentiate this y dot m, I get the y component of the velocity. But what's y dot? Y dot is minus VA. Is minus VA. Y dot is minus VA. Right? It's in the negative y direction, so minus VA. And VA and VB are known from those equations. So the velocity of the midpoint is going to be VB by 2 I cap minus VA by 2 J cap. That would be the velocity of the midpoint. Right? This is a normal to the plane. There is normal reaction between the plank and the inclined plane. N1. Where N1 obviously balances mg cos theta plus 2 mg cos theta, that is 3 mg cos theta. Right? And there is normal reaction between the plank and the sphere. Is sphere or disk? Sphere? Sphere. Okay, so that's N2. N2 then takes care of mg cos theta, right? Now, the other forces on the sphere, there is going to be mg sin theta. There is mg sin theta, and the sphere is rolling while the plank is moving down. So there is frictional force acting at the interface, and it's going to be static in character. It's not going to be mu2 times n2. It's going to be less than mu2 times n2. So the frictional force, let's say, acting on the sphere, is F. Static friction will act on the sphere. So the sphere is subject to three forces: mg sin theta, n2, and F, relevant forces, right? And of course, there is like a mg cos theta, which is balanced by mg. I'm not representing that. For the Planck, there is 2 mg sine theta. The Planck exerts on the sphere a frictional force upwards. So the sphere will exert on the Planck an equal and opposite static friction downwards. Now, the Planck actually slides on the inclined plane. So the nature of frictional force would be kinetic, which would be like approximately maximum static, which would be like mu1 times n1. Mu1 times n1, that's going to be the frictional force. Mu1 times 3 mg cos theta. Right? Now, under the influence of mg sine theta and f, the sphere has a downward acceleration as. The center of mass of the sphere has an acceleration as, which is caused by mg sine theta minus f, right? M into a. F produces a torque in this sense about the center of mass leading to an alpha. So F into R produces a clockwise, anti-clockwise alpha. This F acting on the sphere about the center of mass of the sphere will produce an anti-clockwise torque F into R. So F into R is 2/5 mr squared into alpha, right? So F would be 2/5 mr alpha. Done with the sphere. Now the Planck. 2 mg sine theta plus F minus mu1 into 3 mg cos theta will produce acceleration of the Planck downwards. So the Planck has an acceleration AP downwards. So we have 2 mg sine theta plus F minus mu1 into 3 mg cos theta would be 2m into AP, 2m into AP, acceleration of the Planck. Clear? Planck. This is all that we can do for the Planck. Now, the closing condition would be the ruling condition for the sphere on the Planck. In this case, I can't say ACM is R alpha because the surface on which the Planck is rolling itself has an acceleration. So there is a revised condition for rolling without slipping. Look, AS alpha. So the acceleration of the point of contact on the sphere would be what? AS minus R alpha. AS minus R alpha, and this must be equal to the acceleration of the Planck. AS minus R alpha must be AP. AS minus R alpha must be AP. That's the complete physics in the problem. So far, so good. Now, what is AS? AS is mg sine theta minus f by m. Yes. So g sine theta minus f by m. What is R alpha? 5f by 2. 5f by 2m. 5f by 2m. The acceleration of the Planck. What's the acceleration of the Planck? G sine theta plus f by 2m. See, this equation will give me acceleration of the Planck. G sine theta plus f by 2m minus 3 mu1 mg cos theta by 2 by 2. 3 mu1 g cos theta by 2. So far, so good. G sine theta gets cancelled. We then have f by m 1 plus 5 by 2 equals 3 mu 1 g cos theta by 2. This is what we have, right? So 6, 3 and 1, 4. 4f by m is this, or 4f, f is this, right? But this is static friction. Static friction between the sphere and the plank. This has to be less than or equal to mu 2 times n2. This has to be less than or equal to mu 2 times n2. Mu 2 times n2, but what's n2? n2 is mg cos theta. So then this equation very clearly gives me mu 1 by mu 2 less than or equal to 8 by 3. mg cos theta gets cancelled. Mu 1 by mu 2 less than or equal to 8 by 3. So the maximum permissible value so that the sphere could roll on the plank is 8 by 3. Maximum value of mu 1 by mu 2 must be 8 by 3. Yeah. A laminar body whose mass is m is being acted upon at a given point P by an impulse J. By an impulse. Capital V and capital V1 are the velocities of the point P. Capital V and capital V1 are the velocities of the point P in the direction of J before and after the impulse. Right? So P has a velocity V and V1 in the direction of the impulse, V and V1 in the direction of the impulse before and after the application of the impulse. So that the change in kinetic energy of the body, that is the work done on it by the impulse, is half of J into V plus V1. Forget that for a while. The lamina has a center of mass. Call that the origin. Call the center of mass the origin. And around the center of mass, build the coordinate axis. Let the x-axis be parallel to J and let the y-axis be perpendicular to J. Right? So, this is the x-axis, and this is the y-axis. And let's say locate the point P by coordinates x, y. Now, imagine that the lamina was in general rigid body motion, before the impulse. The center of mass, let's say, had velocities in the x direction. Its velocity was u1 before the impulse and v1 after the small v1. Let's say this is small v1 after the impulse. The center of mass had a velocity in the x direction, u1 before the impulse and v1 after the impulse. In the direction of the impulse, the velocity of the center of mass will change. Whatever the impulse does is reflected in the velocity of the center of mass. Right? Along the y direction, the velocity before and after the impulse will not change because there is no component of J in the y direction. So it's not going to bring about any translational velocity in the y direction. So if it was Vy before the impulse, it remains Vy after the impulse. Vy is the velocity of the center of mass in the y direction before and after the impulse. Why Vy can't be changed by an impulse perpendicular to Vy, right? General rigid body motion means it must have had an omega also. So before the impulse, let's say its angular velocity was omega 1, and after the impulse, let's say its angular velocity was omega 2 was the angular velocity after the impulse. Impulse in this direction will bring about change in linear momentum in this direction. So J would be v1 minus u1. Yes or no? J would be m into v1 minus u1. Impulse in this direction will bring about change in linear momentum in this direction. So J m into v1 small v1, right, minus u1. So far, I'm not talking of the velocity of the point P. I'm only talking of the velocities of the center of mass in the direction of the impulse and perpendicular to the impulse. Now, this impulse, which is acting y units from the origin, this impulse J, which is acting y units from the origin, produces a clockwise angular impulse, J into y about the center of mass. Yes or no? This J produces J into y as the clockwise angular impulse, right? About the center of mass, it produces J into y as the clockwise angular impulse. So, what does J into y do? Is change in angular momentum about the center of mass. Change in angular momentum about the center of mass. So, that's ICM into omega 2 minus omega 1. No? Angular momentum, angular impulse about the center of mass is J into y. That's change in angular momentum about the center of mass, which is ICM into omega 2 minus. The work done by J, would be change in kinetic energy. Work done by J would be change in kinetic energy of the lamina. Very simple. That's what it means. Change in kinetic energy means change in kinetic energy. Change in kinetic energy of translation, so change in kinetic energy of rotation. So in this direction, there is no change in velocity in the vertical direction. So change in kinetic energy, translational kinetic energy is half m into v1 squared minus u1 squared. That's the change in translational kinetic energy, right? Plus half ICM into omega 2 squared minus omega 1 squared. That's the change in kinetic energy of rotation. That's the change in kinetic energy. This must have been the work done by the impulse, right? This you could write as, realize that m into v1 minus u1 is j. So this is j into v1 plus u1, right? This is j into v1 plus u1, half of j into v1 plus u1. ICM into omega 2 minus omega 1 is j into y. So this is like a j into y into omega 2 plus omega 1. This I can write as half of j into v1 plus y omega 1 y omega 2. u1 and v1 are the velocities of the center of mass in the x direction before and after the application of the impulse. Omega 1 and omega 2 are the initial and final velocity, angular velocity, right? Now, at any point, realize that suppose the center of mass had a certain velocity a in this direction, in the x direction, in the direction of impulse, had an angular velocity omega, and this was the point P at x comma y, right? This point P in this direction will share a common velocity a with the center of mass. In addition, because of omega, it will have omega times L. Omega times L as the tangential velocity, right? Which means now the velocity of the point P in this direction would be a plus omega L cos theta. Velocity of the point P at such a juncture is going to be a plus omega L times cos theta in the direction of the impulse. A plus omega L cos theta. theta. What is L cos theta? L cos theta is this length, which is y. L cos theta is y. So this is a plus omega y. So if a is the direction, a is the velocity of the center of mass along the x-axis, then for the point P, the velocity along the x-axis would be a plus omega times y. So very clearly, in the initial state, when the center of mass had a u1 and had an omega 1, the velocity of the point P is going to be u1 plus omega 1 times y, right? Which is given to be v. And finally, it had like a u2, or rather a v1 plus omega 2 times y. That must be capital V1. Finally, this is before the impulse, this is after the impulse, v and, right? So v and v1, capital V plus V1.